I will begin with a word of prayer. So, dear Father, we thank you for this day. Thank you for the students. Just pray you to guide our work today, Lord. In your name I pray. Amen. So you guys, if you're not, I'm only halfway done grading your test. I will not turn it back to you today. So, whatever happened, happened. If you would get out a sheet of paper and write your name at the top, that will be worth 10 points to you today. So,
You said 100 points?
I said 10. 10 points. 10 points. 10. So, we are now... yeah, we could do one piece of paper with a bunch of names on it. That'd be fine. Sorry, it's too late. So, I will... Maybe one for each row. I can take like 5 papers. You guys figure it out. I'll make sure your name is on a piece of paper that gets to me anyway. All right. So, yeah, that's the bonus quiz. I actually really meant bonus quiz. I mean, what's that? If you write your name twice. If you write your name. If you write your name twice, I will give you 5 points for each time. In calculus. Only write your name if you're here. That goes without saying. Let's see here. Okay, so theorem. This is theorem 10.1. And I'll be honest, I don't know this stuff by heart, but I think it's worth writing down because you might not have ever seen it. And I personally would probably have to look it up. It just doesn't come up that much in what I do. I don't know why, but here it is. The standard form, but I'm mostly writing it out so when you guys go to do the homework, you're not alone. The standard form of the equation of a parabola, all right, with vertex h comma k and directrix y equals to k minus p is, here it is, x minus h quantity squared plus, equals 4p times y minus k, right? Or for a horizontal directrix, x equals to h minus p, we have y minus k quantity squared equals to 4p times x minus h. All right. So there's two different kind of parabolas, right? There's the ones that open up and there's the one that's open sideways. The ones that open up will have a horizontal directrix. The one, I should say, what? Oh, I'm sorry, I got tricked. This is a vertical. I was mixing, he has the axis for the parabola labeled, and I was reading the vertical for the axis rather than the directrix when I wrote that. Yeah.
Is that a 4P or
4p. Here. Now, the coordinates of the focus are what? Coordinates of the focus. Let's see, for the first one, with the vertical axis, the are at h comma k plus p. And on the other one, the coordinates of the focus are where h plus p comma k. All right, fine. So how's this, what's this look like, right? I'll draw one that opens up, try to illustrate all the different things going on here. Let's see here. So we have two things. We have a directrix, which is k minus p, right? So if this is I guess I'll make this y equals to k minus p. Where's the focus? It's supposed to be at k plus p, right? So I'm starting to regret. I'm going to make this k. I'm sorry, guys. I'll make up my mind eventually here. I'm going to let this be y equals to k minus p. I'm going to let this be y equals to k. And then k plus p would be up here. So there's focus at k. Oh, stink. I always assume the stupid thing is on the the y-axis, but that was dumb because it's not assumed to be there, is it? So that's easy enough to fix for me. There we go. Sorry. So there's your y-axis, here's your x-axis. Focus is there. Where was it? Again, it was at h comma k plus p. And k minus p is the directrix. Now, how is the parabola related to the directrix and the focus? Like if you had to, define the parabola geometrically, what would you say about, what makes a point on the parabola a point on the parabola? Yeah.
Aren't all the points on the parabola equidistant from focus and directrix?
Ah, there we have, that is exactly it. So it's a set of points that are of equal distance from the line, which is the directrix, and the focal point. Now, you might ask the question, what does it mean? How do you define distance from a point to a line? How should we, if I take this point, how far is it from the line? There's this line, there's that line, right? Those have different lengths. How far is the point from the line? Well, we understand that to mean what? This distance, right? The closest, the minimum distance. When we have extended objects, we define distance to extended objects by the closest distance. So one of the points that would be on the parabola, we're looking for equal distance, right? So that puts one point on the parabola right here, right? That's definitely one of the points on the parabola, right? And what happens then if you move up, if you get a little bit equal distance from the, you said equal distance from the focus and the directrix, right? So if we bend, it's going to look something like, I never can draw it worth anything, but it's something like this, roughly speaking. If I did that right, anytime you look at the distance from the focus to the point, right, we'd have the same distance down here, right? So like this, if I drew it right, this distance would be the same as that distance, and so forth. But there you go, that's how to define a parabola geometrically. Now, if I can draw it again down here for the sake of my drawing. If this parabola has a focus somewhere in here somewhere, right? Where do parabolas come up? One of the places they come up is in the study of geometric optics. Do you guys know what geometric optics is? It's studying light with geometry, basically. So there you imagine coherent light rays, and you imagine coherent light rays coming in and hitting. This could be like a mirror, all right? I'm thinking of it as being a parabolic mirror, which is meaning that it's got a cross-section which is a parabola, right? Which means it has this focus. And if you imagine light rays coming in like this, when they hit the mirror, what happens is they go through the, oh goodness gracious, I think I have drawn it badly. Oh, this is not how I should think. I mean, well, I need to time reverse this. Imagine this. Imagine this is the a star. Here's a star. This is a rather unphysical example, but imagine a star. I mean, a point source of light here, okay? And then what happens is if you put a star here, then the light would go off like that. So if the light originates at the focal point, it hits the parabola and it all goes off. When it hits the surface, it just goes off straight like that. Sorry, I don't usually talk about this in here anyway, so I'm going to stop. But this is, of course, one of the places where parabolas are interesting is in the study of geometric optics. You'll do more of this in your Physics 232 course, but for the moment being, these equations should suffice, right? If we want to find a parabola with a particular focal point vertex, I think we have the equations we need to do it, right? Let's look at an example. If we look at y equals to x squared plus 4x minus 2, find the directrix, focal point, and axis of symmetry. All right. So I'm going to, let's see here. I guess to use my theorem directly, I need to do some kind of algebraic monkey business here to make it look like this, right? So what are we stuck with? We have to isolate x on that side, right? So if we look at this, we've got y. I can put the 2 on the other side, right? So that's y plus 2 is equal to x squared plus 4x, like that, right? And let's see here, then complete the square. What do I get? X plus 2 squared. Then I've added 4, right? So I have to subtract 4. And so you see that this equation can be rewritten as x plus 2 quantity squared equals to, what have we got here? Y plus what? Y plus 6. All right, so if we look at this over we have now fit the theorem, right? So if you compare this, so now we just kind of have to basically do pattern matching. We've got x minus h squared equals to 4p times y minus k, right? So if we multiply that out, what's that give us? That gives us 4py minus 4pk, right? So the coefficient next to y is, the meaning of it is 4 times p, right? So if we look at this, right, it has to match that, which tells me that p is equal to, p is equal to 1/4, right? Right? And what else can you say? I mean, I can also see, without more work, I can see that h is equal to what? Negative 2, right? And what else? K is negative 6. I'm not saying you're wrong. I need to work it on. So we've got 6 is minus 4 pk, right? But we already know that 4p is 1. So that's equal to minus k. So I think what you said is right. You said k was minus 6? Is that right? K is minus 6. I'll bite. All right, so let's collect our thoughts. What is the, can we talk about the vertex? I usually think about the vertex of a parabola. Oh, he's got that in the, I failed to remember what I wrote. Here it is. So the vertex is where? Okay. What did you say it was? Minus 2?
Yeah, minus 6.
Minus 2, 6. The, oh, minus 6, sorry. And what else do we got here? Where's the directrix? Y equals to what? K minus P, which here is minus 6 minus, what's P? Minus 1/4, all right. So using decimals, as is not usually my custom, minus 6.25. There you go. But that helps me to make graphs, of course. And what's the axis of symmetry? I think we'd have x equals to minus 2. The axis of symmetry goes to the vertex. So it's just x equal to the x coordinate of the vertex. That's the axis of symmetry. So I think I have more than enough to graph this parabola, right? Now, I don't always cover this material in Calculus 2. I thought today I would try to give it a shot and see what it feels like. And I mean, it's okay. It's okay, but this is really not that big a part of what we're doing. Bad.
How come the line's not only vertical, not only horizontal?
I'm sorry?
Like that one, you drew it like horizontally.
Oh, just hold on a second. So minus, this is mine. I'm just setting up my grid. So that's minus 2. Then about 3 times that. It's down here. So here's the minus 6. You know. So that's the vertex is at minus 2, minus 6. This thing opens up, right? And where's the directrix? It's down here, right? Just below that. So where's the focal point? I neglected to find that, but that's right here, right? So the focal point would be at minus 2, comma, minus 5.75, right? Because it's the same distance from the vertex. You know, you go to the vertex, the same distance from the directrix to the focal point on either, you know, it's halfway between the directrix and the focal point. So that means that's there. And then you can attempt to graph this thing. But you know what? I'm going to cheat. And by cheat, I mean I'm going to look at x squared plus 4x. See, because I find this method of graphing to be insufferable because we know all kinds of things about functions and graphing, and we're not using any of those, and that feels very wrong to me. For example, to find the vertex of this parabola, what I would do, usually, is I would calculate f prime of x, and I would get 2x plus 4. I would then set that equal to 0, because that's where the graph has a turning point, right? And so that would imply that x is equal, 2x is equal to minus 4, so therefore x is equal to minus 2 at the critical point, right? Calculating f prime prime of x, I would get 2, which is greater than 0, which would tell me that it's a minimum. This is a far better way of thinking about this function. I'm sorry, I really don't like, I understand why the book is doing what it's doing, but to me it feels wrong to divorce ourselves from all the things we know in Calculus 1. So, I mean, it's a great theorem. It gives you precise, but the calculus won't discover where the directrix is, right? It won't discover where the focal point is, but it will give you a good picture of what the graph looks like with like a lot less effort. How about continuity? What does continuity help us with? Can you factor this? I think algebra does a fair amount there. This is x plus 2, quantity squared, right? Minus what? Minus 6, right? So this is x plus 2 plus the square root of 6, x plus 2 minus the square root of 6. So algebra reveals to me that the x-intercepts are at minus 2 plus or minus root 6. What's root 6? 2 point something, right? So it's got x-intercepts like here and here and here symmetrically. See, if I know where the x-intercepts are, and I know where the vertex is, then I can graph the stupid parabola, right? So I don't need all this. I don't need all this highfalutin directrix and focal point and all this nonsense. I mean, the directrix and the focal point, they're lovely, but I don't need them to graph a parabola. I need them to really understand, from a geometric optics perspective, what's going on. To have a deeper understanding of what the parabola looks like, that's great. But if I'm just after graphing, I certainly don't need Theorem 10.1. Just saying. All right, I got that out of my system. Here's an example for you. I think this should be enough for you to do the homework. I'm going to go on. Why am I talking about parabolas? I have foolishly tried to follow the book this semester, which I regret wholeheartedly. You should never follow the book in your teaching. You should always follow your heart. It's better. So, parabolas, ellipses, and hyperbolas, these are all what? These are all what are known as conic sections. Right? That's because if you take a cone, which you might think is this, but you'd be wrong, it's this. Right? You got to include you might call it double cone in the usual vernacular. If you take that and you slice it with different planes, you'll either get ellipses, hyperbolas, or parabolas. You can also get lines, right? If you take this and you imagine slicing the double cone with like a plane, depending on how the plane hits it, you're either going to get an ellipse, a parabola, or a hyperbola. That's why they're called conic sections, because they're sections in the sense of cutting a cone. The one I can draw, kind of, is this one. So that'll be like an ellipse where it cuts. Anyway, generically, yeah, exactly. Generically speaking, the that's why I brought this thing. There you go. So, if you study ax squared plus bxy plus cy squared plus dx plus ey plus f equals to 0, all right? This is more or less, well, this is a quadratic equation in x and y, right? It turns out every conic section, all right, if you just look at the plane, if you think about this being like the yx plane, start this way. Think about that being the yx plane. You can write the equation of the conic section as the solution set to an equation of this form, right? They're all like that. Whether it's a line or it's a any of these, they all fit into this context. Now, this xy stuff, that's above our pay grade. You need linear algebra to do this. For this, you need rotated coordinates, right? But standard, so right now already, I've assumed that the parabola either opens vertically or horizontally. You can talk about, but you see, you guys, you can have parabolas that do this, right? But if you have a parabola that does that, if it opens the symmetry axis is not vertical or horizontal, what's the equation for a parabola like that? It's not one of the ones stated in Theorem 10.1. All right? Nor will I tell you what the equation is. This is something you have to discover with linear algebra, where you can discuss rotations of coordinates properly. That said, ellipses, well, you can also have that problem for ellipses, hyperbolas, any of these things. Like an ellipse could look like this. It could be on a slant, you know? Hyperbolas could also be weird. They could also be on like a slant. But the standard one, ellipse or hyperbola, I have no working markers today. I have to keep throwing them away, otherwise they keep coming back to haunt me. So ellipse looks like this. It's the solution set of x squared over a squared plus y squared over b squared equals to 1. This is what an ellipse looks like. All right? Hyperbola. It looks like x squared over a squared minus y squared over b squared equals to 1. Or it looks like y squared over b squared minus x squared over a squared equals to 1. If it opens horizontally or vertically, all right? So these you need to learn how to graph them and to identify them and see them coming. And of course, I've done what? I've centered these at the origin. You know, we can make it uglier. What would we do? So this is centered where? Yeah, 0, 0. Again. It's like a conspiracy against myself. I have I have so many markers, but they have like all run out in the same day. I have no working black marker somehow. It's driving me nuts. Guess we'll have to go blue. All right, so example. If we have x squared minus y squared equals to 1, what's that look like? So first of all, the way I think about this is to find asymptotes of the hyperbola. I just think about, x. I look at x squared minus y squared. Look at x squared minus y squared equals to 0. That will give me the asymptotes. All right. And so that's not easy enough to see that that gives you y squared equals to x squared, which gives us y is equal to plus or minus x. Those are my asymptotes here. So asymptotes are what they sound like. They're things that the hyperbola will approach but not get to. Okay? Now I just have to figure out which kind of hyperbola it is. It either opens up and down or opens left and right. Right? Which is it? Up and down, why? If it was up and down, if I put x equals to 0, right, then that should give me minus y squared equals to 1. Right? But there are no real solutions to that, right? So 50-50. Sorry, didn't work out for you. But it's sideways opening because we can have y equals to 0, right? What happens when we put y equals to 0? We get x squared is equal to 1, which gives me solutions of x plus or minus 1. These are the so-called vertices of the hyperbola. So it looks something like this. All right. Am I boring you guys? Have you guys seen these things before? Who's already comfortable with what I'm doing and I'm wasting your time? Are you just enjoying the not doing series right now? Yeah, okay. All right. I'm still grading your test. You could at least pretend to be interested. All right, example. Anyway, another one here would be something like y minus 3 squared minus x plus 2 squared equals to 1. Here's another one. This one is going to be a hyperbola because it's got a difference of squares, all right? But it's not centered at 0, right? Where is it centered? Minus 2, 3, right? Asymptotes. What's the asymptotes here? How do we find the asymptotes? Yeah, replace the 1 with a 0. And the reason to do that is because if x and y are really, really big, the 1 is irrelevant. So this is basically assuming that x and y are both, really, really large. The absolute value, let's say. I don't care about signs. So suppose that x and y are both much, much greater than 0, then we can neglect the 1. I mean, that's an intuitive way I think about the asymptotes, but whatever. Anyway, solve this equation. We get y minus 3 squared equals to x plus 2 squared, which gives us what? Y minus 3 is equal to plus or minus parentheses x plus 2, which is to say that y is equal to 3 plus or minus x plus 2. So those are your asymptotes. Minus 2, 3. So and that's easy enough. I mean, they look perhaps, I don't know what they look like, but they're lines with slope plus or minus 1, so that's easy enough to do, right? Sorry, this one's still a lot like the last example. I could do better with my variety of examples. And now you got to decide, does it open left or right or up or down? Them's your choices. Left and right. You should not gamble. What's that? Is that wait a minute, is that a criticism here? I mean, what is our official position on gambling here? Is gambling okay? What does the Liberty Way say about gambling? Are we allowed to gamble? What's that? Well, only with math homework. Oh, you were saying something before I started.
Yeah, that's a stronger brother.
So you could remember, right? Just what you said. If it's well, we just did this one, right? X squared. This was horizontal. I mean, that's not wrong. This is vertical. But see, the thing is, I invariably, and you're right, it will be vertical, but I invariably forget. So I just go back to basic principles, which is to check, right? So like the axis of symmetry here. I mean, if I cut the line in two, what is this? This x equals to what? X equals to minus 2 is right there, right? So does this equation have a solution at x equals to minus 2? If it does, then it opens vertically. If it doesn't, it opens horizontally. So just plug in. If we plug in, it's too hard. What do you mean? X equals to minus 2 gives me y minus 3 squared equals to 1, which tells me that y minus 3 is plus or minus 1, right? Which it gives me more information, too. It also tells me that the vertices, the places where it opens, are either what? 4 or... I'm sorry, minus 4, right? Wait a minute, I can't do math. Yeah, 4, or what'd you say? -2? That feels wrong. That feels wrong. I think 2. I think 2. You guys are trying to trick me. Sometimes math, you go, Daddy, you're tricking me. Let's see here. So I think that was roughly speaking there. Anyway, so long story short, this is your badly drawn hyperbolus. That's what you said? Oh, okay. Yeah. It's good. It's good.
Couldn't let him have his moment.
I know.
I shot him down. Tragic. Oh my God. It's Friday.
It is Friday. I'm so ready to be done. I have 3 tests this week.
Thanksgiving is always
So good.
You guys seem very content right now. I feel like I should ruin that. Let's see here. Example. Just let you go early. How about this? X squared plus 4x plus y squared minus 6x equals to 0. Let's figure out what this is. So this is x plus 2 squared, right? And I did what? I just completed the square. I have to subtract a 4 to be fair, right?
I'm sorry.
You know, just because you did that, I'm going to add an 8. I'm going to add an 8. I'm adding an 8. And I'm changing that to a y. See what you made me do. So now I'm going to have to actually think. So that's an 8. I'm going to have to factor that 8 out. And I've got a y squared minus 6/8 y, right? Like I gotta factor that 8 out so I don't get into trouble. Now, okay, so this is x plus 2 squared minus 4 and then plus 8 times y. That's, what's half of that? Yeah, y minus 3/8 parentheses squared, right? Minus 9/64 equal to 0. So what we got? We got ourselves an x plus 2 quantity squared plus 8 times y minus 3/8 quantity squared equals to, and I'm going to bring that 8th downstairs. I'm going to write that as 1 over 8. I'm going to write this x plus 2 as over 1, although it's kind of dumb. I'm going to do it. And what do I get? On the other side, I got 4 plus what? Oh, I did that too soon. I'm sorry, guys. I retract my stupid comment. What is that? 9 over 8. I believe I have a winner. So this is also known as, what, 32? Oh, man, just like I planned it. Check that out. Wait a minute. Oh, no, it's not as good as I thought it was. 32 plus 9 is what? 41. I made a mistake and it came out to 40. I was like, oh, cool, it's 5. No, it's not 5. It's 41 over 8. All right. So here we go. X plus 2 quantity squared over, let's see here, 41 over 8 plus y minus 3/8 quantity squared divided by 41 over what? 64. Multiply equals to 1. So this is an ellipse, right? It's centered at where? Right? And if I were to draw a picture of it, foolishly, attempt such a thing, it's roughly speaking here. And what is so this has an a equals to the square root of 41 over 8. This has b equal to the square root of 41 over 8. Heh. It sounds the same, but it looks different. And which means what? Which one's bigger, a or b? B, right. A is bigger. We should always go with your second answer. Is that a rule? It's funny. So if we, let's see here. If you put x equals to minus 2, right, what happens with y? Plus or minus square root of 41 over 8, right? If you put y equals to 3/8, you get x is equal to plus or minus the square root of 41 divided by 8 inside the root. So that tells you the semi-major and semi-minor axes of the ellipse. Let's see here. So this one's a little bit more, I don't know. Can you guys tell me what these are numerically? I'm kind of, that's about 6 point something or other. This is roughly 6.3 over 8. This is roughly the square root of, which is what?
That's 0.80.
0.8, 0.8. And what's the other one? Square root of what? Square root of 2 point something? 2.3?
Yeah, 2.3.
All right, so what that means is that it's, curses, this is, so it actually, it goes like, it's something like this is the picture then. So there you go, that's a very bad picture, but kind of a roughly correct picture of the ellipse, which I would not have been able to tell you if you just asked me, what's this look like, graph it. Like without algebra, I'd be, there's no way I could figure that out without algebra, right? Okay, this is just the start of what we're doing, all right? This is just picturing some of the curves we want to play with. What we're actually interested in is understanding these curves parametrically, which means we need to find parametrizations for these curves. In other words, you want to be able to write y and x as functions of time, where time is the parameter. Now, fortunately, I have enough time to do that. So what is the parameterization of this curve? Check it out. For this one, I would set x equals to hyperbolic cosine of t, and I would set y equal to hyperbolic sine of t. Why would I do that? Pretty simple. If you take these formulas and you try them out, we've got x squared minus y squared is what? Cos squared minus sin squared is 1, which means what? That means that if we pick a time, t, and we pick cos and sinh of t, then that pair, x comma y, actually does land on this curve. Right? That makes this a parameterization of the right half of the hyperbola. Notice we know that cos t is greater than or equal to 1, right? So this is just a parameterization for the right branch. If I wanted to parameterize the left branch over here, I would use x equals to minus cos t, and I would use y equals to sinh t. That would be a nice parameterization of the left branch of the hyperbola. Okay. How about this one? What I would do is I would put y minus 3 equal to cos t, and I would put x plus 2 equal to sinh t, because, you know, if I did this trick once, I can do it twice. See, because if I set that as cos And if I set that as sinh, then cos squared minus sinh squared is 1, which means that these formulas will serve to parametrize half of that hyperbola. Of course, to clean it up, y is equal to 3 plus cos t, and x is equal to minus 2 plus sinh t. There you go. These are parametric formulas, or it's a parametrization as it's called, parametrization of half the hyperbola. Which half? Is it the upper half or is it the lower half?
The bottom half.
Oh, it was the top half. Because this is greater or equal to 3 plus 1. The key is that the cosh is always larger than 1. So that shows you that y is beyond 4. So this is a parameterization. It's a parameterization. Man, it's almost impressive. Goodness. Now, guys, so great. We know cos squared minus sinh squared is 1. Now I want to parameterize the ellipse so we can leave here. Well, I won't leave here, but you'll leave here. What would you do? I mean, what do you know that looks like this algebraically? We know cosine squared theta plus sine squared theta is 1. So that informs my creation of a parameterization here. All I do is I put x plus 2 over the square root of 41 over 8 equal to cosine theta. And here I put y minus 3/8 divided by the square root of 41 over 8 equal to sine theta. You solve those equations for x and y, you got a parameterization for the ellipse. So, what I'm trying to tell you is if you really think about it, you can use cos and sinh for hyperbolas, and you can use sine and cosine for ellipses. You just have to think about it.
Is that why it's called hyperbolic sine?
That is why it's called hyperbolic sine. Indeed. And that's why sine and cosine are sometimes called circular functions. Although, I mean, you just stretch it out a little bit. But
Do you use sine and cosine for parabolas or without?
for parabolas,
Whatever.
whatever. We'll talk more about that next time. And the truth is, you can parameterize a given curve in infinitely many different ways, so there's not really just one answer.